Hi everybody and welcome back to my SP2 channel. This lecture is all about the first law of thermodynamics. It does have a lot of pieces, but I think we can go through pretty much all of them pretty quickly. It's pretty straightforward. We're going to be looking at the first law of thermodynamics. We're going to be looking at the systems and surrounding, what is our internal energy, and then how we can relate that to the heat and work, a little bit on the endo and exothermic process, what is the state functions, and we also have a practice for you at the end. So looking at the first law of thermodynamics, take a look at these few simple events. Let's say you drop a stone down a deep well. So what does that mean? That means you're practically converting your gravitational potential energy into your kinetic energy, right? Or let's say this is winter time, it's pretty cold, we'll try to warm our houses. So what do? We are using the natural gas, right? And we are practically reacting the natural gas with the oxygen, so we are converting the chemical energy into heat. In both of these examples and every other that we can imagine, right, the energy is always going to be converted from one form to another one, but we're not going to create any energies, right? We're not going to destroy the energies either. So this is exactly what I have for you for the first law of thermodynamics, which is the fundamental principle of energy conservation, stating that the energy cannot be created or destroyed and only transferred or transformed, right? And this is something that would apply to all the physical and chemical processes around us. Now, in order to follow our discussion for the energy changes, we are typically focusing on a very limited and well-defined part of the universe, right? That's how we can zoom in to keep track of the energy changes. So we call that the system, right? So our system is going to be always the portion that we single out for a study, and that system may be open, maybe a closed, or maybe an isolated system. So these three terms, they have a very defined explanations. Okay, so starting by the open system. In an open system, both matter and energy can be exchanged with the surroundings. Okay, but if I have a closed system, then energy can exchange, right? No problem for the energy, but matter cannot exchange with the surrounding. Okay, and then in your isolated system, neither energy nor matter can be exchanged with the surrounding. Now, what do I mean when I say surroundings? Guess what? Everything else, right? So whatever is your system, and then everything else is going to be the surrounding. So let's say you're doing a chemical reaction in a container. That container would be your system. And then the bench that you put your container on a bench, right? That bench, the lab, the whole campus, the whole universe, right? The rest of the stuff is going to be your surrounding, right? Okay, I hope that makes sense. Okay, so the next topic is going to be our internal energy, which is typically goes by E symbol, and that is our system's energy, the total energy, which is going to be the sum of your kinetic and your potential energies of the component of the system. Now, in our thermodynamic discussion, we are mainly concerning with the change in our E, okay? By which I mean, you can start by looking at your starting point, right? Your initial energy. And then your system is going to undergo some sort of changes, which might involve work being done or heat being transferred, right? And then you're going to have your final energy state after the change is done. And then your delta E would be the difference between your final and your initial. So anytime that you hear about delta E, or let's say delta, that means you're interested in the change before and after the reaction, right? So we go by E final minus E initial. Okay, so keep that in mind. Delta is always final minus initial. Now, for all of our thermodynamic quantities, such as delta E, there are going to be three parts that we are interested in. They're going to be a number, they're going to be a unit, and they're going to be a sign. Okay, so the first two, which is the number and the unit, are going to give us the magnitude of the change. And then the third one is going to give us the direction. Okay, so what do I mean by that? Let's say your final energy is more than your initial energy. If you take the difference, that is going to give us a positive change. So you can say your delta E is greater than 0. But if your final energy is less than your initial energy, we're going to have a negative change. The delta E is going to be less than 0. So I'm going to demonstrate this on the next slide using a very simple, diagram as well as a real chemistry example. Okay, so follow me on the next page. Okay, so let's say that I have my internal energy unit axis here, okay? And this is going to be your initial stage, okay? You start from this point. So if you ended up having lower energy, right, when you do your reaction, that means the final state of your energy would be less than your initial state. This means that the energy lost to the surroundings, right, so that you can say we have negative change or negative delta E, okay? Now, from the other side, looking at here, let's say your final stage has more energy than the initial one. This means that the energy is being gained from the surrounding, and we're going to have a positive energy change, okay? Here is an example in chemistry. If you are mixing hydrogen and oxygen gases, and this is your initial state, at the end, we're going to form water, right? This is our liquid water. And as you can see, the change here would be negative because the energy level for your water, for your product, is less than your reactant. So I can say my initial energy is more than my final energy, and therefore energy is released from system to surrounding, and therefore we are expecting to get a negative energy change. Okay, cool, cool. Okay, so if you remember, we talked about heat and work in our previous lecture. So this slide is going to be considering how we can, relate our delta E to heat or work. Okay, so I want to ask you to think about your internal energy as your bank account. So you can do deposit or withdrawals, and that can be done in the form of either heat or work. Okay, so if you do deposit, then you're going to increase the energy of your system. That would be a positive change in your energy. If you do withdrawals, then we're going to have decrease in the energy of our system, which means that we have a negative change. Okay? Now, if you remember the algebraic expression for the first law of thermodynamics, we said delta E goes by Q plus W, which is heat plus work. Okay, so when heat is added to a system, or if the work is done on the system, then the internal energy is going to increase. Both of these are examples of, depositing money in your account, right? So if you add heat to your system, that means you deposit money, right? Or if the work is done on the system, you are still depositing your money, and therefore you can increase your bank account, right? Okay, now I'm going to show you this table on the right side to go over the signs, because remember, signs is always important, right? Okay, so if I have a positive heat, that means my system gains heat. But if I am losing heat, then it's going to be a negative heat. For work, if I have positive work, that means the work done on the system, right? And if I am having a negative W, that means the work done by the system on the surrounding, right? So all of these positive examples are going to be like depositing your money, and the negative cases are like withdrawals, right? Now, your delta E is going to be the net gain of energy by your system. If that's positive, right, we got net gain. If that's negative, then we're going to have net loss of energy by the system. Okay, so if you want to pause here and kind of review the table before we do the practice at the end of the session, that would be super helpful. Okay. Okay, now because the heat transfer to and from our system is always kind of important for our discussion, we need to like specifically determine how we can describe the direction of our heat flow. Okay, so in chemistry, If we have a process in which the system absorbs heat, we call that endothermic process. Very simple example would be melting of the ice, right? The heat flows into the system from surrounding. So if we touch the container where we have the ice melting, the container feels cold because heat is transferred from our hand to the system, right? Now, on the other side, if you have a reaction, if you have a process in which the system releases heat, we call that exothermic. And during an exothermic process, such as combustion, right, that's a really common one, the heat flows out of the system into the surrounding. Okay, so endothermic, absorbing heat by the system, exothermic, absorbing the heat by the surrounding. Okay, cool, cool. Okay, so the next important term in thermodynamics is the state function, and we're going to go over this concept using a very simple analogy. Okay, so let's say that you are planning to travel from one city to another one. There are different ways that you can do that. Maybe you can drive your own car. Maybe you can go to the airport and fly, right? Maybe you can bike if you're very athletics, right? Or even walk. So there are different methods, and the method by itself really doesn't matter. What matters is you want to reach to your destination. You want to get to that city, no matter how you get that, right? This is exactly what I have for the concept of state functions in our thermodynamic discussion. State function is a property that depends only on the initial and the final states of the system and not the path that we are taking to get that. It's not depending on the reaction mechanism, another way of saying that. So some of our thermodynamic quantities, such as energy, are state functions, okay? Some others, such as heat or maybe work, are not going to be state functions, okay? So it's important to know what are the functions that are a state function in our thermodynamic discussion, okay? So think about your delta E, your energy, that is going to be the sum of your Q and your W, right? So we know that the delta E depends only on the initial and final states, but the individual values of Q and W is going to be dependent on the path, right? So let's say you change the path of your reaction, okay, in a way that you increase the heat transfer, right? So your Q goes up. Now your W has to go down by the same amount, right, in order to maintain your delta E without any changes, right? So this is something that you always need to keep that in mind, that your energy is path independent, but your heat and work are going to be path dependent. Okay, so that brings us to our practice. Okay, so consider this genetic reaction. We have two gases, A and B, reacting, and they are producing a solid C. Now, it seems that we have a kind of cylinder piston setup, right? And it says the system loses 1150 joules of heat to the surroundings. Okay, so the system loses energy, right, to the surrounding. Now the piston is moving downward. Okay, the gases are, reacting and they are forming the solid. As the volume of the gas decreases under the constant pressure of the atmosphere, right, the surroundings do 480 joules of work on the system. Now the question is, what is the change in the internal energy of the system? Okay, so I need to take them one at a time. For my heat, right, in terms of the sign, is going to be a negative heat because heat is transferred from the system to the surrounding. So that's a negative energy, right? But for the work, it should be positive because work is done on the system by the surrounding, right? That must be a positive value. And then you just need to put them together. You've got your delta E, Q plus W, right? We have negative 1150 joules, and you add that to your 480 joules, and that is going to give us a negative 670 joules. So that is a negative change in our energy, right? That means the starting of your, the energy of your starting system was more than the energy that we have at the end of this process. Okay, cool, cool. That is it for this lecture. Thank you very much for watching this video. You know what to do, right? If you like it, you can definitely give a thumbs up to that. You can share that with your friends. If you're enjoying the content and you want to keep learning with me, just go ahead and hit that subscribe button. It means the whole world to me if you support me. Okay, if you guys have any questions or maybe there's a specific topic that you would like me to cover, you can always comment that below. Thank you so much for your support, and I'll see you soon on the next video. Take care and bye bye for now.